All right, we are doing AC circuits today. We did DC circuits a couple of chapters ago. So today what we're going to do is, to our circuit, we're going to connect an AC source. And these two chapters will become a whole course. And essentially these two chapters are based on the two Kirchhoff's laws, okay? So let's get with it. So what we'll do is we'll connect a resistor to an AC source. We'll connect an inductor to an AC source. We'll connect a capacitor to an AC source. And then we'll connect all three in series. Okay. And we want to see how they behave. So we're going to keep it fairly simple. All right. So, all right. So let me show you what an AC source looks like. So an AC generator converts mechanical energy into electrical energy. Okay, so let me show you an AC generator. Okay, so here's an AC generator. Okay, so this AC generator has a permanent magnet, and you have a loop of wire that is rotated. This loop of wire can be made to rotate. At a dam, it's the flowing water that makes it rotate. In a windmill, it's the blades of the fan that are rotating because of the wind that's making this rotate, and so on. We talked about this in the past. Okay, so there's that loop that rotates. Okay, so you could also do the following. You could have the loop stationary and rotate the magnet. So you could do one of the two. Okay, so you can either rotate the loop or rotate the magnet. Okay. Now in the US, the frequency, the number of cycles, see, this is one cycle, and in the US, the number of cycles per second is 60. Okay, so the frequency is 60 hertz, and so this has to be rotated 60 times a second. And it's very important to maintain the frequency constant, and the frequency is maintained constant to within 1%. Okay. In Europe, the frequency is 50 hertz and so on. Okay. So here's an AC source, and this voltage is given by described by a sine function, sine or a cosine function. Okay. So now what we're going to do today is we're going to connect this kind of source to our circuit, okay? And this is called an alternating current source. Okay. So this is the voltage we're going to connect, and this kind of voltage is gotten out of this kind of device, so AC generator. Now, devices such as light bulbs and toasters work equally well with AC and DC currents. However, it turns out motors are more easily adapted to AC currents. And like I've said before, a sizable fraction of our work is done by electric motors. So also the angular frequency of the EMF is equal to the angular frequency of the loop. So the frequency of this voltage is equal to the frequency of the loop. Okay. I'd urge you guys to read this article. That'll show you the importance of keeping the frequency constant. Okay. All right, so here's this AC voltage, and this is the electrical symbol for an AC voltage, a circle with this squiddle. Here's the AC voltage, and the voltage is given by a sine or a cosine function. Okay, you can use a sine or a cosine function. There's the amplitude of the voltage. Okay, so there's the amplitude of the voltage. And omega is the frequency. Omega is 2 pi f. So let's go to the whiteboard. Omega, the angular frequency, is 2 pi times f. And f is the linear frequency. In the US, it's 60 hertz. Okay. And in Europe, it's 50 hertz. So your voltage source is V0 sine omega t. Okay, and now in the US you get 110 volts out of your wall socket. That is VRMS, which is Vmax divided by root 2. Okay, so this is 110 volts, and times root 2 will give you Vmax. Okay, so in the US, the amplitude of the voltage is 110 times 1.41. Okay, so about 155 volts. Okay, so that's the amplitude of the voltage. Okay. All right. So that is the source we're going to connect. So there's the AC source, and we're going to connect it to various circuits. Okay. So here's the idea. So this summarizes what we want. So here's an AC source, and we'll connect it to a circuit like this. And what we are interested in is the following: what is the amplitude of the current coming out of the source? Okay. Now, also when you do your circuits class, you will be interested in the current flowing through each device, which you'll solve. Okay, so you'll be interested in the current flowing through each arm of the circuit. But here's another thing we're interested in. We're interested in the amplitude of the current, total current being drawn. And you see, this is called a phase shift. You're interested in this phase shift. Okay, so let me go to the whiteboard and then okay. So we'll start off with a simple DC circuit. Okay, so here's the DC circuit. Here's the resistance. Okay, and here's the EMF I R. So in this circuit, I is equal to the voltage divided by R. Okay, and if you connect, all right, if you connect an AC source to this circuit, you'll see that, the current will be, voltage is sinusoidal now, sine omega t divided by R. Okay, so the current is also sinusoidal, I naught sine omega t, where I naught is V over R. Okay, so the amplitude of the current is that. Okay, now if you connect an AC source to a general circuit, okay, so I'm going to draw it as a black box. What you're interested in is your V is, your voltage is amplitude of the voltage times sine omega t. And the current is generalized as V naught divided by Z sine omega t minus phi. Okay, so the generalization of resistance is called impedance. Okay, Z is called impedance. So let me write that down. Z is the impedance of the circuit, and that's the generalization of resistance. And phi is the phase shift of the current to the voltage. Okay, so in a general circuit, so in this circuit, the current amplitude is Emax divided by Z. So for a circuit, we are interested in what is the resistance of this circuit, and the generalized term is the impedance of the circuit. Okay, so there are two things we're interested in. We are interested in the Z of the circuit, and the phi of the circuit. And you'll see that term phi, the phase shift, what it'll tell you is how much power is being consumed by the circuit. Okay. So it's related to that. And so, for instance, if phi is, phi can take a value between minus 90 and plus 90 degrees. And if phi is 90 degrees, minus 90 or plus 90, no power is being consumed by the circuit. Okay, so we'll come to that. So anyway, so there are two things that we want to know for a circuit. So we'll connect an AC source to this black box circuit. And what we want to know is what is the Z of the circuit and what is the phi of the circuit. You know? And again, where do they come in? Vt is V naught sine omega t, and It is V naught over Z sine omega t minus phi. Okay, so these two quantities that come in here in the expression for the current is what we are interested in finding for the circuit. Okay. All right, do you guys understand that? Do you have any questions at this point? Anybody questions? And by the way, I imagine you could hear the dogs in the background, right?
A little bit.
Yes.
I'm sorry?
Just a little